Hello everyone. So far I discussed in this current chapter current electricity. So first we define that electric current. So current I equal to the rate of flow of charge dq by dt. So its units are amperes. Then after we discussed about conductors which offers very less resistance to the flow of electrons. So we define Ohm's law. Volt is directly proportional to current for a given conductor and V equal to IR. So we introduced a new character that is known as resistance. Resistance R equal to V by I, which units are ohm. So this resistance is material property. If material is changes, the resistance value gets changes. So we define conductors and insulators. So conductors are those which have very less resistance, which offer very less resistance. And insulators are those which offer high resistance. Now later we talked about resistance factors affecting the resistance. The resistance is directly proportional to length of the conductor and the resistance is inversely proportional to area of cross section. Together we have written resistance is directly proportional to L upon A. So resistance is equal to rho times L upon A. So here we introduce another character. So that is nothing but resistivity rho. So rho, we define that rho equal to resistance times area upon L, if you can remember that. So its units are ohm meter. Resistance offered per unit meter. So this is defined as resistivity or specific resistance. So this is also a metal character, a material character. If you change this material, so material to material, this character gets changes. Its value will changes. So after resistivity, we define as current density. Current density. Current density J equal to current per unit area I upon A. So from this we can write another formula for current. Current I equal to the dot product of current density times area, which is also you can write the dot product of two scalars. So you can write that J dot A cos theta. J A cos theta. So J, we define that in terms of current per unit cross sectional area. So from this we can write that units ampere meters inverse 2 is the units of current density. Later we define that conductance. Conductance which equal to G, it is nothing but the reciprocal of resistance. The reciprocal of resistance is known as conductance. Its units are ohm inverse or Siemens. So after conductance, we define that as conductivity. The reciprocal of resistivity, conductivity we can show as sigma. Sigma is nothing but the resistivity of the reciprocal of resistivity we define as conductivity. So its units also comes under ohm inverse and meters inverse are the units of conductivity. And the last concept which I discussed about vector form of Ohm's law. In the vector form of Ohm's law, we derived the relation between electric field E equal to rho times J bar. So we define this as a vector form of Ohm's law. So these are the concepts so far I covered. Today I would like to talk very important concept, that is nothing but drift velocity. The concept of drift velocity. The concept of drift velocity and relaxation time. Very simple concept and important concept. What is this drift velocity? We know that suppose if I take a conductor, suppose if it is a conductor which can show in the form of a metal. Now it is having free electrons. Now in this conductor electrons are free, so they are free to move. Now due to because of thermal motion, because this conductor is at in room temperature, so these electrons they move in very random, so they have their own directions, and that motion is due to because of the temperature. So they can move as they wish. This electron will go in this direction and this go and this go, if you can take any random direction. So these all electrons they wants to move as their wish. And if we take the algebraic sum of the total velocity of the electrons, if this velocity equal to u1 and this is u2 and this is u3, like that up to un, the algebraic sum, the average velocity u1 plus u2 plus u3 and un upon total number of electrons n, which equal to 0. So their algebraic sum will become 0. So they do not contribute any current due to because of that random motion. Suppose if I change the scene, suppose I am having same conductor. So let me first make a conductor. Now if I take this conductor with in the presence of electric field, one more final. Oops. Yeah. Now to this conductor, let imagine here I pasted a positively charged plate and here a negatively charged plate. Or otherwise you can just imagine that here I applied a potential difference. Here I applied a potential difference. Now when the external electric field is applied, just think about that electrons in this conductor. Now the electrons in this conductor, they will affect due to because of the external electric field. These all electrons in this conducting material, those are affected by the external electric field. Now due to because of that, now these all electrons they started to move in one particular direction. If they started to move in one particular direction, that contributes to us current. And here, since they are starting in one particular direction, so the total velocity is not equal to 0, because they are not colliding each other. They are not colliding with the atoms, they are not colliding with each other. So there is no concept of collision since they all are moving in one particular direction. Now that contributes something which is known as drift velocity. So here our task is to find what is this drift velocity. So let us find that first, and before that I would like to show one small animation regarding this motion of electrons. Suppose if you take a conductor, in a conductor the atoms, especially if you can take copper, and they are having very free electrons. If you can closely watch, the free electrons are moving due to because of thermal motion, temperature, and they are moving very random. They will move throughout the lattice and they will in the positive ions, and they contributes to collisions. Free electrons in a conductor, they always continuous random motion. So if you can see, they are these different electrons are in the different directions. So they all are in different directions, and when they are in different directions, when they move, and they all will move in the different directions. Now the total velocity or the random motion and the total energy contributes at here goes to 0. Now the velocity of free electrons due to thermal energy of the conductor is termed as thermal velocity, and this is happens till if these electrons do not contribute any current for this. Not only that, this electrons number is more in a conductor. Due to this random motion, the electrons will suffer collisions with the positive ions in the conductor, and so they frequently the net flow of electrons in a particular direction is 0. So the electrons contribution, current contribution at this case will become 0 because they are not moving in one particular direction. If we calculate their average velocities, the total average velocities in this particular case will becomes 0 because of they are moving in random directions. They won't contribute any velocity. So but when we can change the situations, suppose to this conductor, if you can apply an external electric field by applying a potential difference across the conductor to this conducting material, if we connected a potential difference, so that potential difference do something change. So here it is the potential, it's the positive potential, and here it is negative potential, and electric field direction from positive to negative direction, and if L is the length of the conducting, and V is the potential what we applied at here. Now what is the direction of electrons if we can take? So the direction of electrons, they will move from positive to negative inside the conductor. Now they will move in one particular direction, and that direction is due to because of the external electric field. The external electric field set up in the conductor from positive to negative. So now the electron starts to move. The electrons starts to move opposite to the direction of the electric field. Since why they are moving? Because they are experiencing certain force. So here I would like to write what is the force experienced by the electron. We know that force F equal to QE QE, the product of charge and electric field. So here the charge is nothing but electrons, so I can write F equal to minus E times E. I think if it is less visible, I can increase. I can write that force F equal to Q times E, the product of charge times electric field. So here my charge is electron, so I can write that Q equal to minus E times E. Now this is the force experienced by the electrons. If this is the force, what about the acceleration? How we can write acceleration? From Newton's law, F equal to ma. So these two are forces, we shall make it equal. Therefore, ma equal to minus E times E. Now from these expressions, can we write the accelerations? Acceleration A equal to minus E charge of electrons times electric field upon mass. So this is the acceleration gained. That is the acceleration, not gain, that is the acceleration of the electrons within the electric field. Now because of these accelerations, what the electrons do, they will drift, they will move towards the positive plate. So that is our final task to find out. So if I write that expression at here, in the presence of electric field, each electrons experience a force. How much they can experience a force? We know the formula, F equal to Q times E. So this is the force and electric field relation. Here charge is nothing but electrons, since Q equal to minus E. So I can write that F equal to minus E times E. That is the force experienced by the electron. Since F equal to ma from Newton's second law, so if we can make it equal these two forces, F equal to QE, so minus E times E, and F equal to m times A. So our expression will be changes that m times A equal to minus E charge of electron times electric field. Therefore, I need to find out here acceleration A equal to minus E times capital E upon mass. So this is the acceleration of an electrons. Let it take my second equation, and if I take this average velocity, this as the first equation. Now that is the acceleration. Now here we need to define to find out that velocity. So let me say how I am planning to find out the velocity. So if you remember from the first equation of motion, so that is equal to V equal to U plus AT. If you take initial velocity equal to 0, and A is the acceleration and T is the time, and V becomes as our final velocity. So here T we define at here as relaxation time. So we define that as the average time that takes or elapses, the average time that elapses between two successive collisions. The average time that elapses between two successive collisions of an electron is called as relaxation time. So this is something not new for us. We already studied in the molecular motions and all. Relaxation times, what it really means is, so within the electric field, in the absence of electric field, what happens? The electrons used to collide. After collision, their direction gets changes. So here we need to define a parameter called as a time, so that is nothing but relaxation time. According to definition, it says that the average time, the average time that elapses or takes between two successive collisions. Between two successive collisions. Suppose if I draw a diagram at here, suppose I am having electron. So this is my electron, and here some other electrons are there. Now this electron is in motion. For a moment, we can just imagine that this one electron is in motion. Now this electron is in moving. It went up that here, it collided. So after collision, so it changed the direction, again it collided. Now the time taken between these two successive collisions, successive means back to back. The time taken between two successive collisions, that we define as relaxation time. So if this one, for this electron, so this electron you can give a name, so the electron name is this one. So for the time took by this electron to collide this another electron, that we define as tau 1. And for another electron, for the other electrons, it takes as another tau. So likely it is taking as another, so like that it is taking up to tau n. Now if you can take that average, here you have to take that average time. So tau equal to tau 1 plus tau 2 plus tau 3 and so on, tau suffix n, because we consider n number of electrons upon total number of electrons. So let me write it properly. So this is small n. Now the time taken between two successive collisions, that we have considered as relaxation time. Now here we have considered that as total time. So this is only nothing but relaxation time. Now during the relaxation time, what happens? The electrons gains the velocity. So that velocity only we need to find it out. So during the relaxation time, tau, the electron gains the velocity. So that is given by, velocity is given by, that velocity we are calling as drift velocity v suffix d, which equal to, so this is nothing but, as per I said, v equal to u plus at. You can take initial velocity as 0, so initial velocity goes to 0 plus acceleration a times t becomes tau. Now I got the acceleration value here from second equation. Acceleration a equal to minus e, charge of electron, times electric field upon m. So drift velocity v suffix d equal to 0, take it out, no problem, and acceleration a equal to minus e times e upon small m upon tau. Now if we can write Vd equal to minus E times E upon by M times tau. So this is the drift velocity expression for an electron in an electric field. So if that electric field increases, the drift velocity is also increases. Not only that, when the relaxation time decreases, the drift velocity is increases. And here the negative sign tells about the velocity is having direction. So the negative sign tells about the velocity, the drift velocity direction is opposite to electric field direction. Since the electrons are moving opposite to the electric field from this expression. So from this figure, if you can see, the electrons are moving just opposite to the electric field. Here the electric field direction from the positive charge to negative charge. But the electrons are moving within the conductor from negative charge to positive. Negative potential to positive potential. So that's why the drift velocity is opposite to the direction of the electric field. So the parameter V suffix d is a vector, drift velocity is a vector, we're supposed to mention that, and here the electric field is also a vector. So the parameter drift velocity V suffix d is called drift velocity of electrons. It may be defined as the average velocity gained by the free electrons of a conductor in the opposite direction of the external electric field. So this is the velocity gained. So this term is little weighted. It is the velocity gained by the free electron. How can you say that the electrons are gained that velocity? They are gaining the velocity. Yeah, that is due to because of the presence of the electric field. So if in the absence of the electric field, so in the first figure there is no electric field in this case, so electrons are randomly moving. So the total motion contribution, that collisions, everything goes to zero. Nothing will take place. But due to because of the presence of electric field in the second case, due to because of the presence of electric field, what happens? The electrons are moving in one particular direction, that is against the electric field. Due to because of that, the electrons are gaining. What they are gaining? They are gaining velocity. So that velocity gained by the free electrons, which is known as drift velocity. Now this drift velocity is opposite to the direction of electric field. So this is the all about the concept of drift velocity and relaxation time.